So today I'll be talking about three works. Two of them are earlier papers with myself, Ziyu Wang, and Ying Zhao, and then a more recent work with Daniel Harlow and Ying and myself. And the talk is going to be about quantum gravity in a closed universe. Okay, so we'd like to understand closed universes and quantum gravity. Up here, I have an example of a very simple closed universe that's going to appear repeatedly throughout the talk. So a closed universe is a space-time where the Cauchy slices are compact. So here, the Cauchy slice is a circle. You can see it's this blue slice where if you keep going around it, you get back to your starting point. This is a very simple example of a two-dimensional ADS2 closed universe, which is a Big Bang, Big Crunch cosmology. It starts as at a point, at a Big Bang, it expands out to a maximal size, and then it recollapses into nothing. Okay, so why should we care about closed universes? Well, our universe may actually be closed. I should say we don't know. There have been experimental searches to try to determine if the universe is closed, and all they've done is set lower bounds on the size of the universe. But the true answer is we don't know. But I think if you asked people in the community for their opinions, you'd find that a very common answer is that maybe it's a good thing if our universe is closed. And a lot of the answers, well, a lot of the reasons why people would like it is for simplicity. So if we just look at GR with a positive cosmological constant, a very natural solution is de Sitter space with S3 spatial slices. And we seem to have a positive cosmological constant. Moreover, the Hartle-Hawking prescription is a very natural way to get a closed universe from nothing. So it's a very appealing way to, generate a cosmology without imposing some kind of boundary conditions by hand. Furthermore, if we did live in a universe with some kind of asymptotic boundary, say asymptotically flat space or ADS space, it's kind of, well, strange to explain the origin of the asymptotic boundary. Many people you talk to might say, well, we'd need some kind of explanation for why this boundary is there, etc. None of these are very good reasons for why we live in a closed universe, and of course we don't know, but it's a common belief. Okay, so how do we get to the topic of this talk? Well, in 2019 there was a revolution. The revolution was that we could finally calculate the page curve for an evaporating black hole. Kind of the source of the revolution was we understood the rules of the gravitational path integral. And we understood them well enough that we could calculate many questions about black holes. And the rules we found give us many answers that we really like for black holes. And where that led is that now we have an entire industry for black hole calculations that use the gravitational path integral. We can count black hole microstates, we can do supersymmetric index calculations, can calculate correlation functions and averaged OPE coefficients, et cetera, et cetera. We can calculate statistics of the eigenstates of black hole microstates, and many more examples. So somehow this set of rules is very nice and we like it a lot. And it gives us many answers that we like, even though the gravitational path integral is fundamentally not, well defined from some set of axioms as of now. So how is it related to this talk? Well, if we take these rules that we really like for black holes, and we try to apply them to closed universes, we get a very confusing answer. We find the answer that the dimensionality of the Hilbert space of closed universes is 1. In some sense, the statement has floated around and been known for a very long time, but I feel like it was only during these replica wormhole calculations that the statement started to emerge in maybe a more concrete form. So it was kind of noticed in very many papers, and it was kind of written off as some oddity or something we didn't understand. Many people didn't want to believe the conclusion, and they thought they were doing something incorrect, so they ignored it. Some authors that took it very seriously first were, I think, Merolf and Maxfield. and then after them, McNamara and Vafa. So just to set some terminology, people also talk about baby universes, and there's the baby universe hypothesis, and these are all the same thing, as saying the dimension of closed universes is 1. So when I talk to people, I get 2 responses. People either have known this for a really long time and find it completely trivial, or people think this is totally crazy and this is all wrong. In the first part of the talk, I'm going to try to explain the statement to people that maybe have not heard about it, or would like to know what it actually means, and how we can test the statement through a calculation. So let me first tell you 2 useful ways to think about this statement. Because saying that a Hilbert space is one-dimensional maybe isn't very useful. It's unclear what you should do with that. So in canonical quantum gravity, states are labeled by boundary conditions on a Cauchy slice. So one labeling is by the induced metric and maybe other quantum fields in your theory. On the left-hand side, I've drawn one particular state. It's this funny circle with some funny wiggles, and you should imagine there are also states of matter fields on this slice. Now, we can have 2 distinct states, H and H tilde on the right, where the wiggle is something completely different. Now, if we were doing canonical quantum gravity, as we did, say, in the 1980s, we would, of course, say these states are inequivalent. They're just different states. The new content of this statement is that in full quantum gravity, non-perturbative string theory, whatever that statement means, these states are actually equivalent to each other. So this is one form of the statement. Yes? Not necessarily perturbative. The canonical quantization of gravity on a fixed manifold. So not around some fixed backward. That's right, that's right. This is quantum gravity as it would be written in a 1980s textbook, following, say, what DeWitt developed in the late 60s. Any other questions? Okay, so another useful way to think about this statement, which is equivalent to the first, is that quantum gravity is a unique map from boundary conditions on a slice to numbers. This isn't that crazy of a statement if you think about it from the framework of Euclidean ADS-CFT. In Euclidean ADS-CFT, we fix some boundary conditions for our CFT on an asymptotic slice, the ADS boundary. And we get some unique number for that boundary condition. We get the CFT partition function. We don't think there are multiple numbers for the partition function of n equals 4 super Yang-Mills. This statement is an extension of that to slices that are in the bulk. So not just asymptotically ADS slices, but finite slices in a bulk theory of quantum gravity. Of course, we don't have such a thing at the moment. I should also clarify that this statement applies to Cauchy slices of arbitrary topology and arbitrary space-time dimensions. So it would tell you some crazy statement that a state of a closed universe on a torus is equivalent to a state of a closed universe on some other Riemann surface, as an example.
Can I?
Yes.
So can you expand a little bit on that unique map from boundary conditions to numbers, in the sense that, well, if you have these boundary conditions that form a Hilbert space, that, I mean, maps from that to numbers are just the dual Hilbert space, no? So it's, I mean, I don't understand what is the unique thing or the quantum gravity thing or...
The unique thing. Yeah, the statement is that if you fix, let's say we were doing ADS3 CFT2, and we fixed our asymptotic ADS boundary to be a torus of a particular modular parameter, and we picked a particular CFT. That gives us a unique number, right? It's a very trivial statement. And the claim is there's only one such number with that boundary condition, with that set of boundary conditions. There's not some other number. Sorry? The number is the CFT partition function. But we believe there's some formulation of string theory where we'd sum over bulk geometries with that boundary condition, that would spit out exactly the same number as the CFT partition function. Yes.
But in closed universe, where are you putting the boundary condition, at late time or early time?
You specify any slice,
Oh.
right? So let's draw it. If we had some asymptotic ADS torus, this might be at z equals 0, and you might imagine going in a little bit, and you can specify some smaller torus in the interior here with some induced metric, and quantum gravity would give you some amplitude for this torus. But quantum gravity would also give you an amplitude if you specified some S3 sphere of a certain size with some certain induced metric on it. That's the content of this statement. There's a unique map. There aren't multiple maps. Was there another question? Yeah.
Sorry, just want to make sure I understand exactly what you mean. By unique map, you mean that, first of all, these boundary conditions, you should not put it, I guess, on the same page as an asymptotic boundary condition, in the sense this is a boundary condition defined on a bulk slice.
Yes.
And then you have a map from the boundary condition on the bulk slice, so basically from a bulk state in your, say, effective field theory to some, I guess I'm not sure what you mean to a number. I would have expected that you map a bulk state to a state in some fundamental Hilbert space.
But the fundamental Hilbert space is one-dimensional, which is the space of
you mean
complex
specifically
numbers.
in a closed universe?
Yes.
Oh, okay, because when you say quantum gravity there, I thought you meant in general quantum gravity maps this boundary condition to a number. So in general,
Yes.
it maps it to some state in some Hilbert space. And in this case, you just don't have any Hilbert space. Is that any boundary? Hilbert
That's a
space?
statement, but a boundary condition is, it's a manifold that you choose with a topology and data on it. That's mapped to numbers. So we're always talking about closed universes here. This is how ADS CFT is done usually. This is actually some very old statement. It's basically the statement that string theory is unique and assigns unique amplitudes to manifolds. Yeah.
But I would think of that as an inner product between two such states rather than a single state, right?
An inner product between two such states. Maybe you're asking if I input two manifolds into the map, what do I get? We usually like to interpret this as an inner product, and the claim is that you get a product of two numbers if you do the procedure you just explained. All of this is going to be extremely obvious in 2 dimensions, like just completely obvious, which we'll get to later. Okay, good. Okay, so the statement that there's a one-dimensional Hilbert space appears in conflict with closed universes having non-trivial physics. After all, how can anything non-trivial happen in a one-dimensional Hilbert space? So this seems like a important problem. But if we want to solve this problem, we have to be aware that we want to avoid destroying everything we've learned about black holes in the last few years. So it's not hard at all to solve this problem and get a large Hilbert space. It's very hard to solve it and not completely destroy everything that I had 2 slides ago. So as an example of how I can solve the problem right now, I can just forbid wormholes in the gravitational path integral and proclaim that the right theory of quantum gravity in a closed universe is given by canonical gravity. Canonical quantum gravity as given by textbooks in the 80s, right? That's a fine thing to do, and I get an infinite dimensional Hilbert space for closed universes. But this puts us back to the point where we have a black hole info loss again. So a lot of recent developments have been trying to address this problem while not completely destroying everything we've learned. Okay, so here's an outline for the rest of the talk. I'd like to first present a number of arguments that there's a one-dimensional Hilbert space for closed universes. So I'll start with arguments that come from lower dimensional theories of gravity. In those contexts, the statement is just mathematically proven and true. You can follow everything and it's kind of just like trivial. And people that have thought about these models are going to immediately know that what I'm saying is, not that deep in 2 dimensions. Now, in higher dimensions, because we don't have a full theory of quantum gravity, the arguments are less rigorous, but evidence is accumulating from multiple directions that this statement is true. I think there's some work to do to make the arguments in higher dimensions stronger, but I think they're very suggestive of this statement. Okay, then after explaining the statement, we're going to discuss some options. Is this really a problem? How should we think about it? What should we do? And then I'm going to give a proposal from my paper with Daniel and Ying that, yes, this is a serious problem and we need to do something. And we have the beginning of a solution that we think looks interesting and promising. Okay, I want to first give an argument that's not good. It's based on the holographic principle, and it's very memorable. So the holographic principle states that the fundamental degrees of freedom on a slice live at the boundary. And for a closed universe, there is no boundary. So the holographic principle implies there are few states. Usually it's written as, the dimension of the Hilbert space is e to the a over 4g. And if the area of the boundary is 0, naively, you have e to the 0, and that gives 1, but there's a twiddle. It's not a very precise statement. You're not sure whether it implies there are 0 states, 1 state, 4 states, but it at least implies there's few states. Now, one of the reasons people maybe don't trust this argument is that it's a little unappealing and it proves too much without basically any input, right? There's no calculation. I just said this thing and, hoped you guys would believe it. And now we have calculations that support this statement. So let's now transition to 2-dimensional gravity models where we can actually do a calculation. Okay, so the 2D gravity model we're going to look at today is JT gravity. It's a 2D dilaton gravity model with the following Euclidean action. So what do we want to do if we want to study a theory of closed universes? Well, we follow a number of simple steps. We solve the equations of motion and we find all the solutions. There they are on the slide. They won't be too important, so don't pay attention to them too much. It turns out the solutions are labeled by a maximal size of the closed universe. So this blue slice goes to a maximal size b before recollapsing. And there's also a maximal dilaton value. You can work out the classical phase space. And then quantum mechanically, if we follow the 1980s textbooks, we need to canonically quantize. So we choose a basis. And in this talk, we're going to canonically quantize in the length basis b. So what do we do? If we're given some state psi, which is some superposition of these length b eigenstates with some coefficients, then what we would say is that to see if we're in a universe of some size b, we calculate the probability through this equation, assuming the states are orthogonal. Right? This is just standard quantum mechanics. So for this equation to be meaningful, the states should actually form an orthogonal basis. And how do we check whether states form an orthogonal basis? Well, we need to make a choice of inner product. And the choice of inner product that we really like comes from black hole considerations. So what we do is we specify states on Cauchy slices, right, with their boundary conditions. And we have some gravitational action for our system. And the inner product is going to be defined by integrating over all smooth geometries in between those slices, weighed by the action, summing over all topologies, geometries, etc. The first line is for a general gravity theory. This is exactly what you would do in like Hartle-Hawking's paper. So what happens if we do this calculation in JT gravity? Well, we set up 2 slices where we have geodesics on the top slice of some length b prime, and a geodesic on the bottom slice with some length b. And we do the path integral, and we find it appears to be delta function normalized. Okay, so that looks pretty good. It looks like the states are orthogonal, and we can do quantum mechanics in the way that's in the textbooks. But from these recent developments in black holes, we know this isn't the full story. We know that wormhole effects can be very important when calculating the number of non-perturbatively orthogonal states. So just because gravity might naively tell you two states are orthogonal, you actually have to check. You have to do a more refined check to see if they're actually orthogonal. And there's a very nice way to do this using this gram matrix technology that I believe was introduced by Balasubramanian, Lawrence, Magan, and Sasieta. So the procedure is simple. It's 3 steps. In the first step, we make a choice of a set of states where I runs from 1 to k. So we make a choice of boundary conditions, and these states might be geodesics of different sizes, b1 to bk. Step 2 is we define this gram matrix. So we take the inner product with these states, but we don't do the gravitational path integral yet. We leave it in this abstract form as a set of boundary conditions. Now, in quantum mechanics, if we had this gram matrix, and we wanted to know how many mutually orthogonal states we had in the set, we would just calculate the rank of this gram matrix, right? If we were studying the hydrogen atom, it's possible that some of our psi-I states might be linear combinations of other states that we specified, and the rank of the gram matrix knows if states are orthogonal. We're just doing the same thing, but in gravity. The difference is gravity is a theory that gives us answers that are sort of averaged over some microscopic details. I don't want to explain this, but the bottom line is to do the correct calculation in gravity, we actually have to do a replica trick. So what we do is we take the gram matrix to some nth power, we take its trace, and we evaluate it gravitationally for any n. We want to find an answer that we can analytically continue in n and send n to 0. And the claim is that the rank of the gram matrix is given by taking this replica trick, which tells us the dimension of the Hilbert space. But morally, we're just diagonalizing the gram matrix into eigenvalues, taking the eigenvalues to positive powers, and the rank is the number of non-zero eigenvalues. And this technology, or this technique, has been used in very many works to find that the dimension of the black hole Hilbert space is e to the s naught. So you have very precise calculations of this. The bottom line is if we do the same thing for closed universes, we just get the answer 1. The rank of the gram matrix is 1. And the reason for this is kind of simple and universal and doesn't actually use any details of the theory. It's because the gram matrix for a closed universe satisfies this cyclic identity. If we take g to the nth power and take the trace, it's the same as taking the trace and then taking that to the nth power. In terms of boundary conditions, it's indicated for n equals 3 on this figure. You can see that I have dots with different indices, and because the circles are not anchored to anything, they're states of closed universes, I can just permute them in any possible way, and the left-hand side is equal to the right-hand side. I'm going to give you a short argument and not go through the actual calculation. But G is a Hermitian matrix, right? Because it's an inner product between states. And if you think about Hermitian matrices, if a Hermitian matrix satisfies this property, it either has 0 or 1 eigenvalues. It turns out if you do the calculation in gravity, you get 1 eigenvalue, which is good. And so if we take this limit, we get 1. I haven't done the actual gravity calculation, but I don't want to bore people with these complicated things, but there are papers where you can go look at this, yes.
So there are some particularities, of course, in 2 dimensions. No? So the theory is it has no local degrees of freedom. You could consider it matter.
You could add matter as well.
And so nothing would change this kind of result, no? I mean, you're saying that this in 2 dimensions is completely proven.
Yes,
and,
yes.
It wouldn't change if I add matter, for example?
No, no. I mean, you can see this applies to higher dimensions as well, as long as you assume there's a theory of quantum gravity that is finite and maps boundary conditions to numbers, or assigns some not infinite amplitude to boundary conditions. And we think there is such a thing. And if there isn't such a thing, then we're in bad shape. And this is purely because the boundaries aren't anchored to anything, right? You can move things around freely. Yeah, so the point is that we can do very precise calculations in 2D to like verify this fact both in the bulk and on the boundary. But I just wanted to emphasize that because there's one state, you don't have to do a very complicated calculation to see like a problem in a calculation. Like even the simplest things you try to calculate, you're going to start running into equations that don't make any sense from a Hilbert space perspective. So let's do an example. Let's imagine I have Cauchy slices where I have a little dot that I labeled by I and a little dot labeled by J. They might label states that are like spin up or spin down, some very simple thing. So if we calculate an inner product using the rules, we find that the inner product is delta ij, assuming the states are chronic or delta normalized, right? And this makes sense. A state that's in spin up is not the same as a state that's in spin down. Now, what if we take the modulus squared of the inner product? Now, at the level of cylinder topologies, there are 3 simple topologies we can write, and then many more that I haven't written because they're not important to demonstrate the problem. The first cylinder topology is just double what we had previously and is proportional to delta ij. The second one is 1. The cylinders cross-connect in this funny way. And the third one is this macaroni shape, which gives you another delta ij. Now, clearly this inner product, the second line just like doesn't make sense compared to the first, right? This is totally crazy. This is a kind of a large fluctuation in inner products. And the origin of this fluctuation is it's coming from the fact that there is one state of closed universes, right? And so I'd like to point out that in higher dimensions, the geometries we'd have to include to get these kinds of absurd results are not any more complicated than what we have to include to calculate delta ij in gravity. It's just the same thing but repeated. So in this sense, even in higher dimensional gravity, we can see problems are appearing very quickly. Okay, I wanted to give a boundary perspective on all these statements in JT gravity to just like make it obvious that none of this is very surprising. So JT gravity is famously dual to an integral. So it's dual to an integral over random matrices. The duality state is stated in this first line here, right? So we have an integral over Hermitian matrices with some measure factor that's not important. And we have some matrix integral insertions, so trace e to the minus beta h. The duality works by mapping these matrix integral insertions to boundary conditions in gravity. So the claim is that the left-hand side is equal to the right-hand side, where the right-hand side is a gravitational path integral with some boundary conditions. For geodesic boundaries, the kinds we've been discussing in this talk, the operator that we put in the matrix integral that gives us an answer in gravity is written in the middle line, right? It's this 2 over b trace cos of b over square root h. Now, what does it mean to work in a single theory? It means that we fix the Hamiltonian. We don't integrate over all Hamiltonians. We just fix it to be some random matrix. And now it's kind of obvious that all closed universe states B are mapped to numbers, right? We just input the Hamiltonian into this formula, and then we pick different values of B. And that maps the state to a different number. And if we input many of these O of B insertions into the matrix integral with a fixed Hamiltonian, well, we're not inputting them into the matrix integral, we just get products of the different numbers. This is the origin of the large fluctuations of the inner product. From this perspective, it's not at all surprising that the Gram matrix has rank 1. We're just multiplying different numbers together. So why did we get orthogonal states, or states that looked orthogonal? We got them because we were actually ensemble averaging over theories, alpha states. So in these two-dimensional gravity models, it's not actually true that you have a single closed universe wave function. You have many different UV complete theories of quantum gravity, and it's only after averaging over all of them that you see these many states that are delta function normalized. So people don't believe this will happen in higher dimensional theories of gravity because people want to say that string theory is unique. Okay, so those were lower dimensional gravity models. But I also argued that these weird fluctuations with the inner product can even be seen in matrix integrals squared for low moments. But that by itself is not a proof that the Hilbert space of higher dimensional gravity models is one-dimensional. So here is just a subset of arguments, but we have a few more in the paper. And of course, all of these arguments have, assumptions, and the assumptions might be wrong. But I think it's very suggestive that different lines of reasoning are kind of leading to the same conclusion. And so I think the statement is going to be true in higher dimensions as well. Okay. So an argument by McNamara and Vafa based on no global symmetries. The low-brow version of the argument is that string theory is a unique theory with no free parameters. And it maps bulk boundary conditions to numbers in some unique way. You maybe don't find that very convincing. Well, I don't know what people's opinions are on whether string theory is unique or not, but I find this is a very common opinion. Another argument that's more recent and that I like a lot is based on the Euclidean preparation of a closed universe state by Antonini, Sacchietta, and Swingle in 23. Recently, there was a paper by Engelhardt and Justeau where they used basic features of holography to show that the closed universe state that was prepared in this paper has a one-dimensional Hilbert space. So effectively, just HKLL was used. So if you believe in ADS-CFT and not in, if you believe in just very basic aspects of ADS-CFT, you can argue that closed universes in ADS-CFT have one state, at least in the context of this discussion. We also had an argument in our paper that the factorization of CFT partition functions implies that the Gram matrix has rank 1, but it has rank 1 for a certain subset of states. We're able to prove something a little weaker than what we can prove in one dimension. In 2 dimensions. But that's just a limitation of what we're able to do in higher dimensional gravity. Okay, so I hope I convinced people, or maybe many people already believe that there was one state of closed universes. So now I'd like to talk about the options that people are exploring from different directions. So I think there are maybe 3 options that people are interested in understanding better. The first set of options comes from the assumption if we think string theory really is unique and there is one state. So if you start with this assumption, well, there are basically 2 options. Well, there's one state, so how can there be any physics in a closed universe? Maybe there is no physics in a closed universe, right? Maybe somehow closed universes just are not interested in quantum gravity for whatever reason. And maybe that's the right option, and maybe it's fine. I don't know, but it's an option. The second option is that string theory is unique, and there is physics in a closed universe, but it's encoded in this map from boundary conditions to numbers in some very subtle way that we don't understand at the moment. And our goal is to find a set of rules that would allow us to extract physics of the closed universe from this map. One thing I should mention is that here I've drawn this map as a map from just one state, H, to the real numbers, but you should imagine that I can put in as many slices as I want into this map and get out a number. Another possibility that was heavily discussed in 2020, right after replica wormholes, is that there's actually an ensemble average of theories. There's not one unique UV theory, and each one of these theories has a different closed universe state, and so you get many states. I remember when this was first discussed, there was a lot of disagreement, and people didn't really like the conclusion, but I feel like now people are coming back to this and maybe considering it more seriously. Yes?
I got lost in something. Is the claim that this map exists in quantum gravity and is unique can be reframed by saying that every state in quantum gravity can be formed through some kind of no boundary partition function, like a Hartree-Hawking? Is the same statement?
It's basically the statement, yeah.
But I could imagine constructing states, I don't know, with instead of with no boundary, I don't know, like with some two pants or something.
You want something like this, right?
Yes.
Yeah, the claim is there's a unique map from this to 3 numbers, which gives you the number of this, the number of this, and the number of this. This is what was shown in the first part of the talk in 2D. Right. The point is I can specify whatever boundary conditions I want. Right. I put them into my map, and it spits out the number for the first circle times the other 2 circles, the number you get for the other 2 circles. That's the statement. And if this is true, it's not surprising the rank is 1. Yeah. But again, this would be if you were in the first 2 options, that there's a unique quantum gravity theory with 1 state. Yeah. Yeah.
R? Is the dimension 1 as C or as R?
Technically speaking, it should be C. In all of my calculations, because they're Euclidean, the answer is in the real numbers.
Okay.
But I think in general it should be C.
Okay, and a couple of slides ago you said there was some ADS-CFT argument for this. How does a CFT have a one-dimensional Hilbert space? Sorry.
It's not the CFT that has a one-dimensional Hilbert space. It's a closed universe in ADS gravity.
Ah, okay. Okay.
So, yeah. The construction is by Euclidean boundary conditions, you can form a closed universe that semiclassically looks like it's entangled with a CFT.
I thought you and your collaborators would claim that R is the right answer because time reversal is a gauge symmetry.
Yeah, so I thought about those arguments and they sounded reasonable, but I'm not 100% convinced by them. They sound reasonable, yeah. But also I know how to get complex numbers out of boundary conditions in ADS-CFT, so by introducing like chemical potentials or something like that. Yeah, doesn't matter. Okay, so what's the proposal with me, Dan, and Ying? We're going with option 2, that string theory is unique, this map is unique, there is physics in it, and it's encoded in the map. And we want to somehow extract the physics from this map. Now, as a benchmark, many people working on this problem are now trying to solve the problem of large fluctuations, which comes from 1 state. So that's going to be our benchmark. Can we fix this picture so that the second line is not completely ridiculous? So what's the proposal? The proposal is that we want to include an observer to extract physics from the map. Now, the rule is kind of put in by hand, and the rule and the output of the rule is observer dependent. So what we have to do is we have to pick an observer by hand and condition on them. And our philosophy is that experiments and inner products that we calculate should only be precise to errors controlled by the observer's entropy. So let's try to be a little bit more specific. What are the requirements for a good observer? Well, I think
Sorry, Misha, I wanted to know if you will explain a little bit what exactly you mean by extracting physics from the map, rather than the way I would have thought about it is the Hilbert space that you get out of the map is not the one relevant to describe physics. So I wanted to understand exactly what you mean by extracting from the map.
Yeah. We would like to define a set of rules that only use the map that give us a way to calculate things. That's what I would like to do. The goal is to do calculations and make some predictions. That's the goal. Okay, so to think about observers, we'd like to think of ourselves as observers, right? What would we like a good observer to have? We'd like a good observer to have a large number of degrees of freedom, e to the s observer. We'd like the observer to be in a rich classical environment where they have many pointer states, states that aren't completely destroyed by the environment. And we want the observer to be highly entangled with the environment, just as we are. So we're entangled with the environment in some basis of pointer states. And the observer must also know something about their state. They must know something about their state to feed it into the map, right? We sort of know that, you know, we're on Earth and there's Mars and the Sun and we're in Brazil. So we know something about the geometry, we know something about the metric, the state of the quantum fields, that we can actually feed into this map to get a number back out. If we don't know that, we don't know anything. So we're only going to consider states as defined on the last slice, well, on the last portion of this slide. The little a is an observer, that's us, and I didn't draw the entanglement with the environment, but it's pictorially represented in this state. A is some pointer basis state, and it's tensored with some environment state, and we have some sum over A, which maybe runs over some large index. And maybe we have a spin in a lab, and the spin is in some state I. And what we'd like to do is we'd like rules that allow us to distinguish the state of this spin, right? That's some very simple thing we'd like to do. Oh, and I'm very sorry. I should also highlight that you should see this other paper by Abdallah, Antonini, Iliescu, and Levine for a related proposal on defining observers in a closed universe. Now, I should say at this stage we've done nothing. We've just defined the set of states we'd like to consider. The set of states have some observer, but we still get large fluctuations. So as of yet, observers still can't distinguish different states of the universe. Why is that? Let's forget the spin state for the moment. If we just heuristically look at the observer density matrix, or the density matrix of the full state, without worrying that there's one state for a moment, the density matrix is pure, right? We have this double sum over A and B of the observer and the environment. In quantum mechanics, what would we do? We would trace out the environment, and the environmental states are in some orthogonal basis, and that would collapse this sum to just a diagonal. So the environment would decohere to a diagonal matrix. However, this doesn't work in a closed universe because there's one state. Like different environmental states are actually not orthogonal non-perturbatively. So we need some new ingredient here if we want to get something more than one state. Here's the key step of our proposal. We want to, by hand, decohere the off-diagonal components of the observer density matrix in the low energy description. So I guess in the quantum info literature, this is called a quantum to classical channel. So it's written by this curly C, and by hand, we're just going to act on the observer density matrix and make it diagonal in the environmental basis. So what the channel does is it keeps only diagonal terms in low energy variables. In boundary conditions, what does this do? In boundary conditions, if we were calculating the inner product of I and j, if we didn't do anything on the left, we'd have a double sum over A and B in the environmental and observer basis, right? So the left calculation just gives us a one-dimensional Hilbert space. It gives us answers that are very bad. Once we apply this quantum to classical map, what we do is we correlate the pointer states between the bra and the ket. We've changed the gravitational boundary conditions that we feed into the map. This breaks the product structure of the inner product. This is like the only non-trivial, well, this is the main non-trivial step in our setup. what happens when we correlate the pointer states of the observer and the bra and the ket is this fixes the large fluctuation problem. So if we now do gravity calculations with these new input boundary conditions, I've drawn these lines to indicate that the state on the top and the bottom is correlated in this diagonal way. If you now do gravity calculations, you get something nice. You get an answer you like. The bad fluctuations are now suppressed by the entropy of the observer with their environment. So the errors are controlled by the observer entropy. And one nice feature of this proposal is that as we remove the observer by setting their entropy to 0, if they don't have any pointer states, they're a very bad observer, we get back to the case with a one-dimensional Hilbert space. So we can interpolate between a one-dimensional Hilbert space and a larger Hilbert space. I should also mention one other interesting thing. We did this calculation in JT gravity with matter, or the topological model, and there are also higher topologies you can include. One interesting thing you find is that there's a higher topology that isn't killed off by sending the observer entropy to be really large. So if we try to make the observer infinitely big, quantum gravity corrections, at least in this model, kind of set some lower bound on the fluctuations you find in inner products. This is kind of an interesting structure in the map that I don't think we understand at the moment. But it's kind of telling you that it's not just the observer entropy that, controls how well you can make measurements in a closed universe. There are other features as well. I want to make some final comments. So using this quantum to classical channel is very annoying and, kind of complicated. So if you'd like to simplify things and do gravity calculations in a more manageable way, these rules can be formulated by using an external clone for the observer and the pointer basis. So you introduce some external quantum system called observer prime. It's some regular quantum system. It's not some quantum gravitational system. And you clone the system to also carry the label of the observer. I haven't drawn the environment in this procedure. So the clone is this external line with a blue dot on it. Now, when you calculate matrix elements, when you calculate inner products, the clone acts as an external reference and implements the decoherence protocol I explained on the previous slide. And it's a lot easier to do calculations this way. But I'd like to stress that fundamentally the only input we're using in this talk is that there's a unique map that maps boundary conditions to numbers. And the non-trivial thing we're doing is we're correlating the inputs into the map in a non-trivial way to grow a Hilbert space from nothing. So you usually find a one-dimensional Hilbert space because the inputs in the map are not correlated in any interesting way, which is kind of the source of the problem. Okay, so in this talk we've tried to solve this problem that there seems to be one state for closed universes. And the approach we've taken is we've taken the perspective that there's a unique closed universe state, and we need to manipulate it and the map in a creative way to extract physics from it. Now, the proposal is motivated by decoherence, but the rules are an external input. They don't come inherent to the theory. So I think one very interesting question that a lot of people are interested in is whether the rules can be derived from a more fundamental perspective. This seems kind of hard. Just some more general comments. This problem of a one-dimensional Hilbert space is kind of a problem where all the options seem bad, right? We can either concede that there's no physics in a closed universe, which is kind of a very crazy statement, right? We maybe don't want to concede that. But if we want to get some non-trivial physics with just a unique theory of quantum gravity, we kind of have to go beyond what the theory gives us to get some non-trivial output. And how can we be sure that what we're doing is actually correct when we're putting in things the theory doesn't naturally have? Another option, which I also find appealing, is that maybe quantum gravity isn't unique. And maybe there are many alpha states, and we have ensemble averaging is string theory, and string theory is not unique. But I think the really interesting thing about this problem is that all of these options are bad, but they're bad to different people. So no one likes any particular solution. And I think that's what makes it a very interesting problem. So thank you.
Thanks, Misha. Are there any questions?
Thanks, nice talk. So there is this old idea that de Sitter entropy is related to the area of the bifurcation point of the cosmological horizon. So that says that the Hilbert space is maybe not one-dimensional, but maybe finite. So does not that, this statement is not in tension with your statement that, like, can you comment? Like,
Well, it seems in tension, but that statement was, just a statement. It was something people said.
okay.
It could be that the cosmological horizon is counting the number of alpha states or something. No one knows. There are many perspectives on this statement.
Thank you, Misha, for the great talk. About the clone story. So in this case, I understand the motivation through the coherence, but in practice, I would say the rules are equivalent to having an external reference, right? That is entangled to this closed universe in the semiclassical description. And now you truly have a microscopic system, which is given by this clone, so I have two questions about that. The first question is, would you interpret that clone as some version of the environment the observer is entangled with? That's the first question. The second question is, if you then apply the usual DSCFT rules in the presence of this external reservoir, you would conclude that the closed universe is in the entanglement wedge of that. And what does that mean?
Yeah, I guess it's a closed universe. Well, one statement is, since a closed universe only has one state, it can always be in the entanglement wedge of anything. This was one of the first ways this confusing statement was realized in like 2019, and people were very confused by it. I don't know what to say about that. Regarding the clone and adding an extra reference system, yeah, it's kind of interesting that so to formulate all these rules, strictly speaking, you don't need a clone, but you can add a clone. And it's interesting that adding a clone lets you ask more questions that you couldn't previously ask. But somehow, like for the matrix elements you would calculate, the formalisms give like identical answers. Like the clone is a very simple way to implement this decoherence.
But why shouldn't then I interpret that as actually having, like the point is that the closed universe doesn't have any microscopic system in the fundamental description. Why shouldn't, since the two mathematical formulations are equivalent, why shouldn't I interpret this as saying that what you're doing with these rules is truly having a microscopic system with a non-trivial Hilbert space?
I guess you could think of it that way as well, but you could also think of it in terms of the map. You want to, so fundamentally, if we think the only thing that exists is this map, we somehow want to extract physics from this map. And there are multiple ways to extract physics from the map that are maybe equivalent. I like the clone. It makes gravity calculations easy. I can't complain about the clone. Yeah, I mean, it's in our paper. Right.
Oops. I mean, isn't it a little bit just like the issue of coarse-grained entropy versus von Neumann entropy? I give you some set of observables that I tell you that, I never measure, basically, and then out of a single state, a pure state, there's an equivalent description that has some finite entropy and hence a finite dimensional Hilbert space. And that's more or less what these large N algebras implement automatically, which is probably hidden when you're saying that you're doing semi-classical gravity, because you're just starting with a single, in the microscopic picture, you're starting with a single state and you're building some GNS Hilbert space on top of that, which essentially means, you start with a single state, but then you build up some fictitious Hilbert space that carries all the information that you're interested in. And that new Hilbert space could have like fictitious entropies of various kinds. So, I mean, is this how I'm supposed to understand it? Just, I'm not allowed to discuss certain transitions in this, between different elements in the wave function of the single state, and therefore, it just looks like I have a finite dimensional Hilbert space.
Yeah, I'm not sure I fully understood. I guess the problem is that if fundamentally you have a one-dimensional Hilbert space, it's just unclear at all what you're supposed to do with that to get predictions out.
Well, just say that I think, I mean, decoherence is like saying that you don't allow certain measurements. And when you don't allow certain measurements, then you could split your single state into different components that are, if you allowed these measurements, you could go between them, but now you can't. I mean, that's what coarse graining does. Basically, you say, I'm not going to observe a certain fraction of the operators, and therefore I kind of, instead of working with the pure state, I can work with a mixed state, which essentially means I've turned a single state into a finite dimensional effective Hilbert space description. And that's what I'm asking. I mean, I'm not sure I completely understood the talk, but I'm kind of asking whether this is how I'm supposed to think about this. And well, okay.
Again, I'm not sure I fully understood the question, but one problem people immediately run into is if the Hilbert space is one-dimensional, there aren't measurements you can perform. There's no basis. There's nothing. There are no observables. That's the whole problem. That's why this is a giant problem that many people are thinking about. There are no operators, there's no projections,
Sorry. That's something I know. That's your observable. And I give you that. For that, I don't necessarily need even a Hilbert space interpretation. It's this map. And I go and mimic this via some finite dimensional Hilbert space. Well, okay.
But there's no algebra of operators because there are no operators. So
So I guess this has been said before, but isn't like defining this observer, which is outside, like saying that you are defining some kind of cold boundary, like you are regularizing your closed universe as a bag of gold with a size of the neck, which is what you need to define the observer. Is that the correct interpretation?
The question is whether you should think of the observer as a cold boundary with a finite dimensional Hilbert space?
Or at least the clone.
Yes.
Because you don't apply the rules of quantum gravity to the clone.
That's right. So in ADS-CFT, I mean the ADS boundary is a cold boundary with infinitely many states. And here the clone carries some finite dimensional Hilbert space that is non-gravitational.
Yeah, thanks for the talk. Are these options supposed to be non-compatible?
Well, you're saying there's No physics in a closed universe, but also physics in a closed universe.
With an extra input.
Well, then they're different things.
Well, and you've done two different calculations, you get two different answers.
But we'd like to do a right calculation. Well, that's an interesting perspective. I never thought about that.
It depends on how you define an observer, or just how you define, well, how you define physics.
I thought they were incompatible, but I never,
Any other questions? If not, let's thank Misha again. Thanks.